Right. So after we took roll, I wanted to recall where we left off yesterday, which was this formula for the sum of the interior angles of any n-gon, right? With arbitrary n, you subtract 2 and multiply the result by 180. Why subtract 2? Well, I guess, pick a point, like here, B, right? How many lines can you draw from B that are not currently, so how many diagonals can you draw from B? Well, BA and BC are sides of the polygon, right? So you can't draw those as diagonals because they're sides. And so there you are, that's the -2, right? So with a hexagon, you would be able to draw, can I draw a quick hexagon in here? How about up here? And what is a hexagon? Well, there's different kinds of hexagons. How about like this? So I've got 3 sides, and I want to draw 4. This is terrible. I think I should be using a straight edge, right? And maybe sharpen my pencil. So here's a straight side. Here's a straight side. Here's a straight, that's a little bit straighter now. We've got 1, 2, 3, 4. I need to draw 2 more, right? And how could I draw them? Well, I could draw it like that, and like that. Okay, so there we have that's a hexagon, right? Now it is a polygon because it encloses, the interior is completely enclosed by the 6 sides, right? And we have then 6 vertices as well, right? So here are the vertices. And this is a hexagon. It's got 6 sides. This is not a, sorry, the word is escaping me. Convex. This is a convex. I'm sorry, it's not convex. Why not convex? Well, because for a convex polygon, given any 2 points on the interior, like say these 2 points here, you could draw a line segment which also lay on the interior of the polygon. Can I make this a little bit more contrasty? Okay. And you see these 2 points here and here. If I draw the line segment between them, I have to go outside, whereas that's not true down. This is a convex pentagon, right? Given any 2 points on the interior of the pentagon, the line segment connecting them will also be entirely on the interior, whereas here that's not true, right? So I think this is called concave. But I guess because maybe a little cave is being formed. So now if I were to pick a point like here, A, let's say this is A, B, C, D, E, F. How many diagonals can I draw from A? Well, 4, right? Oh, well, yeah, I guess you got to be careful which point. Is that a diagonal there? Yeah, okay, so that's a diagonal. Here's another diagonal. Here's a 3rd diagonal. And, right, I said 4. Oh, okay, yeah, that's right. So there's 4 triangles, right? So count them 1. So I draw 3 diagonals, and that forms 4 one, that's supposed to be a 2 there. I was thinking 3 was tried to write 2, and then I wrote 3 instead. So this is hard to see here. The third one, 1, 2, 3, and this is the fourth one. So there's 4 interior triangles there, and we then have the sum of the interior angles will be what? Here, sum of interior angles equals what? 4 minus 2, n is, sorry, 6 minus 2 times 180. Okay. And that would be 720. 4 times 18 is 72. So yeah. So that leads to what we want to talk about next is regular polygons, right? Definition. And I think we have the definition in the book, but it's an equilateral and equiangular polygon. So do we have to say both? So equilateral means the sides. Lateral means side, right? So the sides have the same length, and the angles are the same measure, right? An equilateral and equiangular polygon is called regular. So regular polygon. Shall I say a regular polygon? And this is what we're defining here, right? Regular polygon. So is it possible that it's equilateral but not equiangular? Possible as 2 S's. To be equilateral but not equiangular? And the answer to that question is yes. And I can give you a quick example. And this is a special kind of, quadrilateral is what I'm going to draw here. And I'm drawing like 1 inch on each side, okay? And I have to be careful here so that when I draw this, it's going to also be 1 inch, okay? Close enough, right? Use the perfection of your mind's eye. So all 4 of these sides have the same length. That's called a rhombus. So a rhombus is an equilateral quadrilateral, which is not equiangular. Well, that's a good question. A regular quadrilateral is a square, right? It's got all 4 angles the same and all 4 sides the same. That's a square. So is a square also a rhombus? Well, let's keep that question in mind as we go, right? But clearly, this angle and this angle, one is obtuse and the other is acute, right? So that it's clearly not equiangular, right? So the answer is yes, and here's perhaps the simplest example. Now, if a triangle is equilateral, then it's also equiangular, right? In fact, interesting aspect of a triangle, which I know, apropos of nothing here. So let's just note as a sidebar here, in a triangle, the largest side is opposite the largest angle, and largest angle, and So, you know, if we draw a sort of general sort of obtuse triangle here, maybe. So let's call this A. Is this not on the, yeah, A, B, C, in no particular order. So the smallest angle here is this one. The next largest is this one. And the largest is this one, right? Those are all different. So this is a scalene triangle. And it appears that BC is less than AC is less than AB, in the same way that angle A is less than angle B is less than angle C. Right, so they're ordered the same way, right? That the angle that's mid-sized is opposite the mid-sized side, and so on, right? Okay, so if it's equilateral, then it's also equiangular. Does that follow from this? I think maybe in a way. All right, so let's get back to the text and see. Well, let's see. I've got, I guess, one more idea I can pop in here, which is, and this is separate from that, right? So the idea here is that the interior angles of a regular n-gon have the measure, and so what you're going to do is take the total degree measure, the sum of the sum of all interior angles, and divide by n, right? Because each one is the same, and so they must all be 1/n of the sum. Okay, so there's your formula for the interior angles. So should we have an example of these? Maybe we can make a little table. So if so, n is going to be the number of sides here, and then the interior. Sorry. Interior. I'm trying to spell. I'm going to abbreviate interior angles of a regular polygon. Okay. So 360, right? 3 times 60 is 180, right? 4, well, that's 90, right? And 4 times 90 is 360, which is, that's a square, right? So how about 5? Well, the sum of the interior angles is going to be, so if n equals 5, then n minus 2 times 180 divided by n is going to be 3 times 180 divided by 5. And that's going to be, so you want to multiply or divide first, right? If we divide first, we get 3 times 36, I believe. Right? 5 goes into 180 36 times. Sure. So it's going to be 3 times 36 degrees, which is 108 degrees, I believe. So yeah, that's the each interior angle of a pentagon is 108 degrees. So if you bisect it, it'd be 54 degrees, huh? You'd have 2 54-degree. Okay. How about 6? Well, that's a hexagon, and you know, just ask any of your friendly neighborhood bees. 120 degrees, right? Well, let's see why. 4 times 180 degrees divided by 6, and 180 divided by 6 is 30. 4 times 30 is 120, right? So that's easy enough to where I'm not even going to write it out. 7, now 7 is the first one for which we don't get a whole number of degrees, I believe. Let's check that, right? So if n equals 7, then 7 minus 2 times 180 divided by 7. Well, 7 doesn't go evenly into 180, and it doesn't go evenly into 5, right? So you're going to have, I guess, should we multiply here? 5 times 180 is 900, which is also, not unsurprisingly, not divisible by 7, right? Evenly divisible by 7. So should we write it as a mixed number, or what should we do? How many times does 7 go in? Well, 1, and then 2, and then 8, I believe, right? And 4/7. So 7 times 128, is that 896? Yeah, 896, then plus the remainder 4 gives you 900, right? So yeah, we can add that to our table. Okay, 128 and 4/7 as a mixed number, degrees. So that's the septagon. So the prefixes here are pent, hex, and septagon. Is there another one for 7? I think there is. Yeah, then oct is 8. How about an octagon? Does that have a whole number of, yeah, we can write if n equals 8, then 8 minus 2 times 180 divided by 8 is what? Well, that's going to be 6 times 180. And we can reduce by a factor of 2. And then we have 3 times 180 divided by 4. And 180 is actually evenly divisible by, evenly divisible by 4, right? So I reduced 6/8 to 3/4 there. You see that? And then 4 goes into 180 45 times, right? So this is 3 times 45, which is 135 degrees. And so on, right? So we could keep going, the nonagon and the decagon, and I don't know what 11 gets us, right? But yeah, you could fill in the rest of those. But let's go back to the text. You know, we're a little bit behind, I know. And what are we going to do about it? I don't know. Okay, so there we have the definition. And here we have the sum of the interior angles. So this is just what we were talking about. Some of the measures of the exterior angles is also a well-known formula. Let's see, I guess I should zoom out a notch. Huh? Yeah, is that still readable? Yeah. It seems like, yeah, maybe I could make this larger here, right? Yeah, I could. Okay. So exteriors of a polygon can be reproduced together so that they have the same vertex. What are they talking about? Reproduce together so that they have the same vertex. Okay, so you see that angle A here corresponds to angle A prime. Oops, scroll up. Angle A here corresponds, so there's, 1 and 2 on the interior. We sort of bring them all together, reproduce together, right? So you can see that, yeah, as we go along this edge and then turn to the right, we're actually turning through this angle A. And then we're turning through this angle B, and then turning through this angle C, and then turning through this angle D, and then turning through this angle E, and we're back in the direction in which we started. So the sum of all our turns is 360 degrees, which means that the sum of the measures of the exterior angles of a polygon with n sides, whether it's a regular polygon or not, right? It's always going to be just 360. So that's a nice invariant, as they like to say. Polygon angle principles. Oh, we're going to have some principles. Not a lot of principles here. Okay, so there's only two. For any polygon, if S is the sum of the measures of the interior angles, we talked about that, right? That's our formula. Principle 2 says the sum of the exterior angles is always 360, regardless of the value of n. So that's invariant. For a regular, there's the third principle here, which is what we talked about, right? The interior angle for a regular polygon is 180 times n minus 2 over n, right? Evenly distributed among the n angles. And the exterior angle is going to be 360 divided by n. And so notice that the interior plus the exterior does add up to 180. Is that true? Yeah. Yeah, do the algebra. You get a common denominator. You get 180 times n plus what, minus 360 plus 360. So the minus 360 here cancels the plus 360 there. Then the n's cancel from 180 n divided by n, and you just get 180, which is correct, right? You should get a straight angle, right? Interior plus exterior make a straight angle, 180 degrees. That's for a regular polygon with 20 sides. Can you have 20 sides? That's a lot of sides. Yeah, you can have hundreds of sides if you like. And a regular polygon, it looked like a circle, right? Very close to a circle if you have lots and lots of sides. But yeah, so the interior angles, oh, it works out to a nice whole number here. It's 162. The exterior angle will be 18. Okay. They have some solved problems here. Go ahead and read those over. Two new congruency theorems. So now armed with this, so here are our old congruency theorems: side angle, side angle, side angle, and side, side, side. Now we get side angle, angle. And why is that? Well, if you know two angles, you know the third angles. And if you know all three angles in one side, then you have angle, side, angle, right? So this follows from the fact that the sum of the interior angles is always 180. So if you know two of them, you can compute the third. Then that gives you all three angles, and you have a side included between two known angles that will determine the triangle, right? And then there's something here called hypotenuse leg. Hypotenuse leg. How do we prove that? Okay, so let's, I think this one is fairly clear, right? But how about this hypotenuse leg? So if we know the hypotenuse and one leg of the triangle, then we know the triangle. A proof of this principle is given in chapter 16. Oh. Do I have chapter 16? We could look at that if I can find it. So this is, I'm searching through my, oh, so that's not really chapter 16, it's really chapter 15. I misnamed it, I think, is the problem. Yeah. But I've got the whole book here, which we could just get there. So I'm going to open this with Adobe Acrobat. There's the whole book, which I'm happy to share. These are really cheap books, and I mean cheap in the sense that they don't cost much. That's why I like Sham's outlines, because they're inexpensive. Let's put it that way. Not cheap, but inexpensive. So I can go down here to chapter 16. Important theorems, proofs of important theorems. Um, and can I collapse this? Yeah, then we can sort of zoom in on that and see. The theorems proved in this chapter are considered the most important in the logical sequence of geometry. They are as follows. If two sides of a triangle are congruent, the angles opposite the sides are congruent. The base angles of an isosceles triangle are congruent. Oh, well, this is the bridge of Asinorum, right? The pons asinorum is the Latin phrase, and the bridge of asses. Uh, and the sum of the interior magnitude is 180. Okay, two angles of triangle are congruent, the opposite side opposite those angles. So that's the converse of the first one here, right? If the sides are congruent, then the angles opposite the sides are congruent. And if the angles are congruent, then the sides opposite those angles are congruent. All right, so the definition of an isosceles triangle is that the two sides are congruent. From that, we can deduce that the base angles are congruent. Two right triangles are congruent if the hypotenuse and leg of one are congruent to the corresponding. Oh, so that's 4. Okay, so let's maybe jump down here to 4. Although I'm kind of interested in this one as well, right? So we're given that two sides are congruent. That's the definition of isosceles, right? We'd like to prove that those base angles are congruent. Yeah, I'll tell you what, I'll try to post this up. Let's see, I'd have to figure out which pages it is and then save those pages to a file and then post that file. In any case, we'd like to prove that angle A equals angle C. What's the plan? Here's the plan. When the bisector of the vertex is drawn, the angles to be proved congruent become corresponding angles of congruent triangles. Yeah, is that true? So yeah, so if we draw BD, which makes angle 1 equal to angle 2, then we have side angle side, right? Because BD is congruent to itself. AB is given congruent to BC, and the angle here 1 is equal to angle 2 by the construction of the bisector, right? So by side angle side, triangle ABD is congruent to triangle CBD, and that's this step right here. And then corresponding parts of congruent triangles are congruent. Okay, so we saw this proof before, number 2 here. Number 3 is the converse of number, oh, so they're not proving number 3? Oh, here, right. Bottom of this page, can you see that? Oh, it doesn't quite, oh, so let me shrink down my window here so it fits properly. Oh. I don't know what happened. Oh, sorry, wrong window. Okay, so if this fits in here, then I can scroll down and see 3, which is a converse of 1, right? If two sides are congruent, then if two angles, sorry, we're given the angles here are congruent, then the sides opposite those are congruent. The plan here, when you draw the bisector of angle B, again, same construction, right? The sides prove to be congruent, become corresponding sides, but I think now it's angle side. Yeah, BD is congruent to itself. We're given A is congruent to C, and we construct 1 congruent to 2. And so we have angle side, which is now one of our proofs, right? So if we know 2 angles are congruent, we know the third must also be congruent. So we have angle side angle after that, right? So how about hypotenuse leg? That's this one here. 2 right triangles are congruent if the hypotenuse and leg of one are congruent to the corresponding parts of the other. Yeah. Oh, this is pretty clever. Look what they do. So the plan here is to move the 2 given triangles together so that the congruent side BC on one coincides with the congruent side EF of the other. And then since two right angles make a straight angle, the bottom of that is going to be straight, which means that this is a triangle. And it's an isosceles triangle. And so the base angles are congruent, right, by theorem 1 above. And so that means that AB is congruent to DE. And so we have, what is it, side, 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 or side angle, angle? Forming isosceles, the given triangles are proved congruent by using theorem side angle, angle, or angle, angle, side. Well, we know this angle is the same, that angle is the same, and that side is the same, right? So angle, angle, side, sure, that'll do it. Yeah, or you could say, look, if the base angles are congruent, well, we don't know that, do we? We just know that AB is congruent to ED, and of course, BC is congruent to EF. And since it's an isosceles triangle, that means angle A is congruent to angle D. Okay, there's the logic of that. Okay, we can come back to this, but let's go back to where were we here, right? Hypotenuse leg. So we just proved that by going to chapter 16, and I will make that available for you. Selecting congruent triangles using hypotenuse leg or side angle angle. We got a bunch of solved problems there. Let's see, is there new supplementary problems? Okay, these are great. And then we want to look at the my open math problems, right? Yeah, so that's the end of the exposition. Expositionary? Exposition is like the part of the text where they're explaining stuff, right? And then you have examples. Okay, so we'd like to go back to our oh, I see. Oh, that's Adobe again. That's the okay, so we're here. I need to find my window for that. Okay, which is here. And let's see if I collapse this. So was it like, I think I posted that Geometry 4 last week, right? So I move this up to this week. Let's move to week 3 module. Okay, so now it's available up here. Because we haven't really worked these yet, have we? I don't know. I don't think so. And so this one is, you know, you can jump around, right? And find the values of X and Y in each of the corresponding figure. Well, we're given, so how do we know that DE is parallel to BC? It's these arrows, right? Those arrows indicate parallel. That's how you notate parallel lines in a diagram. If you have different pairs of parallel lines, then one gets one arrow and the other pair get 2 arrows, right? So we know alternate interior angles are congruent when a transversal AB cuts parallels. So angle X must be 60 degrees. And I'm sorry, I don't have a way of indicating those are degrees, but you just sort of have to know, right? And angle Y must be 40 degrees, right? Those are also alternate interior angles when the transversal AC cuts the parallels, all right? So here we have that opposite side. So we have, this is a parallelogram. We haven't really talked about parallelograms much, but we will in the next section. Should we maybe jump to the next section at some point? Well, let's just sort of say that 30 degrees is equal to Y, and right, because those are alternate interior angles when the diagonal cuts the opposite sides, which are parallel. And 110 degrees, how can we use that? Well, this angle down here must be the supplement of 110 degrees, which is 70 degrees. So if we know that y is 30 degrees, then x must be 40 degrees. The opposite sides, the opposite angles of a parallelogram are congruent. So maybe I'm sort of jumping here. Maybe maybe we should go, let's come back to this, okay? I want to, what do I want to do? I want to make a copy of this here. Post it in here and then drag it over to be next to, whoop, too far. Oh, okay. And I think we're here, is that right? Oh, no. Sorry, we're here. Okay, so I'm gonna go back. Yeah, leave that page, and I still have this page, right? So, oh, I guess we lost the answers there, but that's all right. So we need 5, and we don't have 5, right? So how do we get 5? Well, we can go to reading section 4, which is this one. Let's move that also up to week 3. So it's there. And if we click on that, we get, oh, sorry, wrong thing. Okay, I want to go to modules. This is supposed to be the reading. Okay, yeah, it is. Okay. And we just want to open this up and change the 4 to a 5, huh? And what are we reading about? We are reading, eventually this will load. Hello, reading about parallelograms, trapezoids, medians, and midpoints, all right? And I'm afraid that chapter, that geometry 4 is kind of depending upon some of the reading in here, which is a little anachronistic. That means out of order. So let's do this, and then we'll be back in order. In fact, I kind of wanted to make a note of this and then add that to our list of readings. So this is, I'm going to add here, external URL. It's this thing. Page name is going to be, what is it called? Trapezoids, parallelograms. Did I miss something in the title? Medians and midpoints, yeah. I want to put a comma here and say comma medians and midpoints. Oh my. Okay. So that's this reading. Let me publish that so you can get the link to that there. How are we doing? Okay. Time flies when you study geometry, it turns out. So I'm going to go back to our Adobe because I think that's probably a clearer way of getting to this. And oh, that's circles. That's the next and last geometry section. But here we are, trapezoids. So a trapezoid is a quadrilateral having 2, but only 2 parallel sides. All right. The bases of a trapezoid are its parallel sides. The legs are its non-parallel sides. So we have bases AD and BC here, and legs AB and CD, right? The median of a trapezoid is the segment joining the midpoints of its legs. So that's MN in this case, right? Okay, an isosceles trapezoid is one with 2 congruent legs, right? The base angles of a trapezoid are the angles at the ends of its longer base. So in this case, angles A and D, since AD is the longer base. And the base angles of an isosceles trapezoid, A and D, right. So in this case, A and D are the base angles of isosceles trapezoid. And you refer to this trapezoid simply by the name of its four vertices, A, B, C, D here. So some principles? Well, the base angles of an isosceles trapezoid are congruent. Oh, can we prove that? Let's see if we, so these are circles here. I think I'm reading, this is, oh, sorry. Oh, I want to see the index on this side. How do I get the index? Having find tools, create PDF, combine files, edit, fill, sign, export, organize, comment, scan, and OCR. There's got to be a simple button for this, right? Not seeing it. Oh, can I scoot it over? Okay, that didn't do what I wanted it to do. Right click on it. I get a context menu you can't see. Show navigation pane buttons. Oh, yeah. Add sticky note, add image. Oh, come on. Document properties, cancel. I'll tell you what I'm going to do. I'm going to close that. I'm going to open it again. So that's open with Adobe. Okay, so then I get my little sidebar again. I don't know what happened to that. Okay, so I want to go to chapter 16 and kind of zoom in on that. Can we find something here? I want to find a trapezoid. Okay, the area of a trapezoid. That's not okay. So that proof is not here. Okay, so how do we prove this? So we try to prove it by hand. The base angles of an isosceles triangle are congruent. Let's give it a whirl. And for that, I want to go to the DocuCam, I believe. Do I have that here? No, because that's annoying. Okay, so we're given a diagram. All right, and I'm going to rotate this a little bit so that it's okay. All right. So I'm going to draw like that and like that. Okay, well, I'll try to make these look isosceles. Okay, so this is in no particular order, A, B, C, D, and we're given that AB is parallel to CD. Okay, we can indicate that with these arrows like so. And we're also given that AD is congruent to BC. Prove that angle D is congruent to angle C. Okay, so we're going to have a statement and a justification. try to make 2-column proof, right? And, you know, I gotta say my handwriting on the board is much better. Sorry about that. Okay. So do we have a plan? You know, I have to stop and think for a bit. You know, I could draw diagonals. Would that do us any good? Well, what if we were to draw this diagonal and we'd have that angle congruent to this angle? We draw the other diagonal. So you'd have alternate interior angles congruent. And you could prove that triangle ADC is congruent to triangle BDC. I think that would be easily enough done. You know, or what if you were to extend AD and extend DC so that they intersect, and then you'd have well, yeah. See, this is tough. This is not obvious to me. Is it obvious to anybody else? Yeah. What's our plan here? I mean, they just give it as a principle, right? But you know, what kind of principle is it? An axiom? Do you have to sort of assume this without proof? That's not what we do for isosceles triangles, right? We prove, right, that the base angles of an isosceles triangle are congruent. Okay, well, let's try drawing the diagonals. We got to do something, right? So I'm going to draw them in different color because, you know, I don't want to make this too messy. So I draw these diagonals, and then my plan would be to show that show triangle, what, ADC is congruent. Can I do that? Do what? Well, ADC is congruent to BCD. That's my plan. Well, we have one congruent side. Do we have congruent angles? Well, I know this angle, because those sides are parallel, I know this angle is congruent to that angle, right? And this angle, we don't know that it's congruent to the other angles, which I think it is going to be, right? But we can certainly show that, right? Because alternate interior angles are congruent. Okay, and then we have angle side. Oh, but we don't know those angles are congruent. Yeah. Well, let's cheat. Well, because time is short, right? And what do I mean by cheat? Well, let's try to get a hint from the internet. So I know that's lame, isn't it? So it goes. And so I'm going to, is it this one? Yeah, okay. And I want to get a document. I think I don't really need this here, so I'm going to say proof, base angles of isosceles trapezoid. Isosceles trapezoid congruent base angles proof, geometry number 150. It's a YouTube. Oh, I don't want a YouTube. Proofs from the book. Okay, what is the book? Well, this is actually a concept uh, developed by I think it was Erdős, Paul Erdős, Erdos, and he said, you know, of all the proofs for a given theorem, which one is the simplest? Then that's the proof that goes in the book, right? Because oftentimes you have competing proofs, and you know some are more complicated than others. Okay, and this is proofs from the book. It's a website, um, and it's the year 2003. I don't know, January 12th. So the overview: a trapezoid is a quadrilateral with exactly one pair of parallel sides. Definitions may differ in sources. The parallel sides are the base, and the non-parallel are the base sides, and the non-parallel sides are the legs. Isosceles trapezoid is trapezoid whose base are congruent, whose legs are congruent. All right, so it's a typo. So much for the book, huh? In this post, we prove that if a trapezoid is isosceles, its base angles are congruent. Okay, so they're saying BC is parallel to AD, we did that. AB is congruent to CD, we did that. In the proof below, we need to show that angle A is congruent to angle B. It's another typo. Jeez. So much for the internets, huh? And so the okay, so proof. Draw the draw the perpendicular. Can you draw a perpendicular? Is that allowed? Sure. Okay. So that gives me a whole new plan. All right. So I'm not going to read any further. I am going to go back to here and go back to my webcam, my DocuCam, right? New plan. So yeah, if your first plan doesn't work, make another plan. And this surprisingly leads to sort of, you know, problematic stuff. But we know that through a point not on a line, there is a unique perpendicular from that point to that line, right? So that is a perpendicular. This is a perpendicular, yeah. And I think now I've got hypotenuse leg. Not necessarily. Oh yeah, well, okay, so we know that, shall I call this AE and BF? How do we know that AE and BF are congruent? Well, the distance, so they're both the distance between parallel lines, right? And so they're both equal to the distance between those parallel lines, and so they're equal to the same things. The things equal to the same thing are equal to each other. Okay, let me try to spell this out. So we're given AB, so we would write this, right? AB is parallel to DC or CD. That's given. And we can construct, so we can draw AE perpendicular to DC. And through a point not on a line, there is a unique perpendicular from the point to the line. Is that okay? And the same justification says I can draw BF perpendicular to DC. Now I'm going to say that AE is congruent to BF. And how do I know that? What justifies that? Well, the distance between parallels is constant, right? Does that say it well enough? I'm going to say it does. Okay, so now I've got AE congruent to BF, and now I'm going to say triangle ADE, and this was, oh, yeah, see, that's not my original plan here, right? But this is going to work for us, I think, right? Triangle ADE is congruent to triangle what? BCF, right? And why? Hypotenuse leg. That's all you need to write there, right? Because we have the hypotenuse. I guess I didn't say, in here I should have said AD is congruent to BC, and that's given, right? So that I should have said that before saying hypotenuse leg, because I hadn't really established that as one of my statements yet, right? But then I have hypotenuse leg, right? The BC and AD are the hypotenuses. Is that the plural of hypotenuse? Or do you say hypotenae? It's one of these eternal questions. I just don't know. Okay, and then the leg AE is congruent to the leg. And shall we write that on the diagram? Make a couple of strokes here and a couple of strokes there to sort of illustrate that those are congruent. And then I can say that angle ADC is congruent to angle BCD. And that's because corresponding parts of congruent triangles are congruent, and that completes my proof, right? Quod erat demonstratum. All right, is that from the book? Maybe, I don't know, if you can find a better way of proving that. Try not to make a lot of typos. All right, so we want to go back to our source here, and where am I then with that? Here? Oh, I think it's this one. Yeah. Okay. Principle 2, the base angles of the trapezoid are congruent, then the trapezoid is isosceles. So that's the converse. And what would the proof of that look like? I think you'd do the same thing, right? You drop the perpendiculars. You can say those are equal. Then all right angles are equal. So you got the right angles are equal. And so you've got angle AB and CD are congruent. The BE and CF are congruent. I'm talking about the perpendiculars, right? So that's two sides, and it's a right triangle. So you got hypotenuse leg again. I'm sorry, we don't know BA. Don't assume what you're supposed to prove. That's like a huge no-no, right? If you assume what it is you're trying to prove is true, then there's nothing to do. That's a bad move, right? So we don't know that BA is congruent to CD. I don't know, shall we? So we'd have that, if I were to draw, should we go back to here? Here's our diagram, right? So in this diagram, we wouldn't know AD. Oh, let me make another diagram then. Oh, we're getting to be short on time. This happens. I could talk about geometry all day and barely scrape the surface. Okay, so if we have an isosceles triangle, I'm going to draw parallels this way. and then fake the okay, so we're given now that this is congruent to that, and this is parallel to that. We want to prove that well, I'm labeling this a little bit differently than in the book. So we're given that angle D is congruent to angle C, and AB is parallel to CD, right? We want to prove that AD is congruent to BC. And if we were to drop the perpendiculars, would that work again here? Let me sort of pencil that in, right? So if I drop a perpendicular here and another perpendicular here, then this would be congruent to that. And this would be a right angle here. So we'd have, so we have angle, angle, side, angle, angle, side, right? So this follows by angle, angle, side. From angle, angle, side, then we would have that the two triangles there are congruent, so their corresponding parts are congruent, and so AD is congruent to BC. All right. Yeah, and so we have 1 minute left. So in that minute, let me do this. I don't know if I can do that in a minute. I'm going to go to our, not there, here, okay. And I would like to upload a file. So I'm going to upload, and then it's going to take me to, you can't see, this is a context menu, which you can't see, but I want to go to where I have this. I just want you to have something to study, because we eventually want to get to, whoops, not there. Eventually we want to get to a test for the geometry section, right? And
Professor, when is homework 4 due?
good question. Thanks for that. I would say by the end of this week, but we still have some work to do, right? My goodness.
Yeah. So do we need to finish reading chapter 5 in order to complete it, or because that's what you said earlier?
Yeah, right. We do. Yeah. And so that's so I'll make it, the end of the week, and so we're gonna have to take up from here tomorrow. So okay, I'm gonna say upload that, and then that's done. And I can go to, where am I? Here. Oh, can I just close that? All right. So I should have that. Yeah. So this is from fall 17, I think. Right. And so I want to go back to modules and add a file, which is going to be a file. And this is just for your consideration. This is not to turn in. But yeah, so there's that, right? And so I'm going to say add item. And here so this is an example of an old test, which we can talk about when we have time, which we don't have time now. So let me ask if there are any other. So yeah, let me go here, and I think I need to edit that. Oh, I think I need to open it first and then edit it, right? I keep forgetting about, oh, and I can't do that because when I open it, I have it available. I will figure this out eventually. So this is that, and And so if I edit it here, I don't really get anything to edit. Right, so it must be that I do this in, yeah, sorry, I'm going over here. I must do this in my open math, huh? Okay. And I don't want to be there. I want to be here. And this is homework 4, which is here. And the settings are here. And do we get a due date here? I don't know why this is so difficult. Yes, you're not able to edit it here. You're not able to edit it there. So let's skip around, show answers. Okay, so I need to go back. So maybe I need to open it first. Well, if I open it, then I'm doing the problems, right? So that's that issue again. And if I go over here and say settings, well, we were just there, right? So that doesn't work. All right, I'll figure it out. Let me address that issue first thing tomorrow, and I will address it right now after class. But I need to wrap this up, folks. Any other questions before? And yeah, thanks for that question, because clearly this is going to have to be dealt with. All right. So have a pleasant afternoon, and I will see you. Yes.
Well, sorry, one more thing. So you just want us to read the whatever's left of chapter 4 and then just go over 5 because you're going to go over it tomorrow, right?
Yeah, that's what we're going to do, right?
Okay, cool.
Yeah, and what you want to do is look at the solved problems in chapter 4 and make sure you see how those work.
All right, thank you. Have a great day.
Okay, you too. Bye, everybody.
Bye, Professor.
Bye, Professor. Take care.
Ciao.